Hello everyone. In this video we're going to go through chapter 5, which is all about multiple random variables, and here we provide an overview. My name is Professor Fred Rispoli. So there are 5 sections. The first 2 cover discrete and continuous joint distributions. The third covers independent random variables, and then the fourth conditional distributions. And finally, we have expectations. So in this first section, joint discrete distributions, we could say if x and y are 2 random variables, the distribution that defines their simultaneous behavior is called a joint probability distribution, denoted by f of xy. And the joint distribution must satisfy that all values greater than or equal to 0. The sum over all possible pairs of f of xy is equal to 1. And if we want to find the probability of x and y in a certain subset A, we want to think of this A as a subset of the plane, then we sum up values over all xy for f of xy. Okay. Now this will be different in the continuous case, but this is the situation for the discrete case. So here's an example. Suppose we have 2 electronic traded funds, ETFs. We'll call the first ETF A and the second ETF B. Think of this as an investment. And let's say we have some sort of estimate that over a period of, let's say, a year, ETF A will return 20% with probability 0.5, 5% with probability 0.2, and lose 10% probability 0.3. And you could see ETF B has returns of 10, 5, and minus 5, and the probability is 0.3, 0.5, 0.2. So we'd like to be able to study the simultaneous behavior of these 2 funds. If we had a certain amount to invest, we'd like to know, what would the best mix be in order to try to, let's say, minimize their loss. Okay. But in order to do that, we need to understand the joint probability distribution. So we'll take a look at that. Now, we know that these 2 funds were independent, okay, or at least close to independent. So if we wanted to find a joint probability distribution, we would take the probabilities we were given, and you can see these are here in the red, and we could simply multiply these. So for example, here, this is the probability A goes up 20%, B goes up 10%. To find the probability that happens, we take 0.5 times 0.3, and we see the probability is 0.15. Similarly, over here, this is the probability A goes up 20%, but now B goes up 5%. So the chances of that happening are this product 0.5 times 0.5, 0.25. Okay, so you can see now this matrix gives us the joint probability distribution, where we're interested in the probability of a change in A and a change in B. You can see that the numbers in here satisfy conditions. They're all greater than or equal to 0. And if you were to add these up, you could see that these all add up to 1. So here's an exercise. Suppose we have random variables x1 and x2, and you have this distribution in here, right? So we know x1 can take on the values 5, 10, 20, x2, 0, 10, 20, and here's our joint probability distribution. So now we're asked some basic questions. Find the probability x1 is 10 and x2 is 10. So 10, 10. So the answer to that would be 0.08. This one over here, find the probability x1 is greater than or equal to 10 and x2 is less than or equal to 10. So x1 is greater than or equal to 10. Those probabilities would be given by these two rows down here. But x2 less than or equal to 10 would be given by these two columns. So to get an answer to this, we would add up the values in this red rectangle, and you could see that these would add up to 0.28. Now, something that we get that's new, the marginal distributions of x1 and x2. Okay, so in this discrete case, we could get the marginal distribution, let's say, of x1 would be the row sums over here. So the marginal distribution for x1 would be 0.42, 0.30, 0.28. From that, we could answer questions like, what's the probability x1 is equal to 5? It would be 0.42, which is just this row sum. And similarly, we could get the marginal distribution of x2. These would be the column sums that you would get down here. And you can see these marginal distributions also satisfy the conditions for a probability distribution. The values are all 0 or positive, and they add up to 1. In the continuous case, okay, we now have functions that we would call a joint PDF. Same notation, f of x1, f of x2, and similar conditions. F of x1, x2 has to always be greater than or equal to 0. And here, if we sum up what happens when we take this double integral over f dx1, dx2, this must be equal to 1. And here, if I wanted the probability that x1 is between some values and x2 is between another pair of values, we get this double integral, where we get x2 from C to D, and x1 from A to B. So we would have this double integral. Now we could also talk about marginal PDFs, right? If I wanted the marginal PDF, we'll sometimes use the notation f1 of x1. What we do is we take the integral from minus infinity to positive infinity of our joint PDF, but we would just integrate with respect to x2. So we're sort of integrating out x2 here. And that's going to give us the distribution for x1. And similarly, we can do this for x2, the marginal distribution with respect to x2. We integrate out x1. All right, so here's an example. Suppose we have a joint PDF, f of xy is 3/8 times x plus y squared. Now here's the region. Think of this as a region in the plane. I'm going to try to stick with rectangular regions. So this would be the region where x is between 0 and 2, y is between 0 and 1. Okay, so if I wanted the marginal distribution of, let's say, x, okay, we might call it f1 of x. So we would find the integral from minus infinity to infinity of our joint PDF. You can see we put it in here. We're integrating now with respect to y. So y goes from 0 to 1. So we calculate this integral with respect to y. So taking the 3/8 out, this would become x times y plus y cubed over 3. Y goes from 0 to 1. So we substitute in the values for y. We leave x just as x. We get 3/8 x plus 1/3. So the complete answer is that f1 of x is equal to 1/8 times 3x plus 1 for x between 0 and 2 and 0 otherwise. You can see here we just did a little bit of algebra to make this turn into this. right? If you simply just multiply through by 3, you get 3x in here, and 1/3 becomes 1. Similarly, we could find the marginal distribution of y. So we sort of proceed in a similar way. We just now integrate with respect to x. So our integral goes from 0 to 2. Those are the limits on x. This is the original PDF. Now integrate with respect to x. Remember, when we integrate with respect to x, we just treat y as a constant. So this becomes 3/8 x squared over 2 plus xy squared from 0 to 2. So here we would get 3/8. We would have a 2 squared, which is 4 over 2. Just simplifies to 2. And x, we substitute in 2 for x, we get 2y squared. So once again, we can do a little bit of algebra here, factor out a 2, and then cancel down here. So this becomes 3/4, and we end up with y squared plus 1, where y is between 0 and 1. So again, these are the marginal PDFs. They satisfy properties of a probability distribution, and they play an extremely important role in this chapter. For example, if you were given the PDF we saw in the previous example, suppose you were asked to find the probability y is between 1/2 and 3/4. Okay, so our first step would be to find the marginal distribution with respect to y. So we did that. We're going to use that here. Right, you can see we go back here. I have 3/4 y squared plus 1. So that's where that comes from. And now my limits of integration are 1/2 to 3/4. So now we work out this integral, all with respect to y. Pretty straightforward, maybe a little tedious, but straightforward. This becomes, well, we'd have a y squared over 2. Okay, but don't forget we have this 3/4 here. When we do some of the algebra, this is what we get, right? So again, we have y squared. We integrate that. This becomes y cubed over 3, I should say. And then when I multiply by 3/4, the 3's cancel. We get y cubed over 4. And then over here, I'll have just a y, but when I bring this in, it becomes 3/4 y. These are my limits. We could work this out, do some tedious algebra, and you see we end up with 67 over 256, or 0.2617 as a decimal. All right, the third section is all about independent random variables, right? So now we have 2 random variables in our PDFs. So the question that comes up often is, are the 2 variables independent? Independence is an important property because it makes calculating a lot of probabilities much easier. So here's an example for the discrete case. Let's say this is my joint probability matrix. The question is, are x1 and x2 independent? So one way to go about this is to check to see if you have the marginal PDF, right? Remember, the marginals would be these row sums and the column sums. And if the product of the marginals is equal to the value in the corresponding cell in here, and if that's true for all pairs, then you know you have independence. It's a bit of a tough way to prove 2 variables are independent because you have to check all pairs. But if you're trying to disprove they're independent, you just need to find one pair for which this fails. So for example, if I picked f1 of 10, let's say. Okay, f1 of 10 and f2 of 20. Okay, so we might call this f of 10, 20 is 0.12. But f1 of 10, okay, if I think about this row sum, it's 0.30. And if I think of f2 of 20, this column sum would be 0.40. So if I try this out, I'd have 0.3 times 0.4. Again, I'm taking this row sum times this column sum. Okay. And when I multiply that out, I get 0.12. I get the same thing both ways. So that doesn't really help me if I'm trying to prove that x1 and x2 are independent. Okay. But if I look around a little bit more, you could see there is a pair where this happens, right? If I take the 10-10 pair, okay, now I know in here we have 0.08, right? So that's f of 10-10. But if I multiply the corresponding marginal probabilities, right, this row sum, still 0.3, and this column sum is 0.23, when we multiply these two, we get 0.069. So since this product is not equal to the stated value, okay, the 0.08, we could conclude that x1 and x2 are not independent. All right, moving on to conditional distributions. Again, this is based on the marginal PDFs. We could say that the distribution of f2 given x1, right? So this is the conditional distribution, f2 of x2 given x1. Okay. Well, here's the way to think about it. Think of this as the original PDF over the marginal PDF with respect to x1. Okay, so this given condition changes things. We have the original divided by the marginal. So here's an example. So going back to this PDF we were looking at earlier. Suppose f of x, y 3/8 times x plus y squared over this rectangle. So we found the marginal, right? We found the marginal with respect to x or x1, 1/8 times 3x plus 1. Now suppose we're asked to find the probability y is less than or equal to 1/2 given x is equal to 4/3. Okay, so we're going to approach this in, just roughly speaking, 3 steps. First, we put together the conditional distribution. f2 of y given x, the original PDF over the marginal with respect to x. So that's what we've done here. All right, we could simplify a little bit. We'll get 3 times x plus y squared over 3x plus 1. So you can see at this point we still have a function in terms of both x and y. Okay. But in our next step, we're going to take care of the conditional part, right? Because in the problem, we're interested in the given case where x is equal to 4/3. So I go back to this function here, and I substitute in 4/3 wherever we see an x. So you get one here, you get one here. Then we go ahead, we do the algebra. You can see 3's cancel. We end up with 3/5 times 4/3 plus y squared. Okay. So a little bit of algebra getting to this point. And we can even take this one more step and think of this as 3/5 y squared plus 4/5. bounds on y, our y goes from 0 to 1, and that comes back from the original. So that's the second step. Now we are ready to find this probability that was the original question. So we could find the integral, go from minus infinity to a half, but we know this really gets changed to 0. This is the function that we have, right? The conditional of y given x is equal to 4/3. And now we could work out this integral, a little tedious, but not too bad. Basically, it's just the integral of a polynomial. And when we're finished, we get 17/40, or 0.425. Finally, we have expectations. We'll just review a little bit. Remember, the expectation of a function of x, in the discrete case, it's the sum over all x values of g of x times f of x. And in the continuous case, we're integrating g of x times f of x dx. So here's a discrete example. Suppose h of x is equal to this function. We get 10 plus 2x plus x squared. We want to find the expectation of h of x. Well, let's say we were given that x just takes on these values, 2, 3, or 4. These are the probabilities. So what we'd have to do is find h of x here first. So in other words, when x is 2, so I want to look at h of 2. H of 2 would be 10 plus 4 plus 4. That's how we get 18. H of 3 is 25. H of 4 is 34. Now in this column, we find h of x times f of x. And here we're simply multiplying what you see over here. So I get 9, 7.5, and 6.8. So if I were to sum up this column, then I would get our answer, 23.3. Now, let's take a look at an example with the continuous case. Again, let's go back to this joint probability distribution we've been using throughout. Let's say I have f of xy is 3/8 times x plus y squared. We know that the marginal PDF with respect to x, right? We found this before, 1/8 times 3x plus 1. So if I wanted to find the expectation of x, just x in this case, here we would have the integral from 0 to 2, x times the marginal, right, of d of x. So I get 1/8. Now I'm multiplying the marginal over here through by x. So I get 3x squared plus x. So we could work this out, do the integral, right? Or we integrate this, we get x cubed plus x squared over 2. And we have to substitute from 0 to 2. And we end up with, I believe, 5 over 512. Okay. So one other thing to know here about expectation. This is an important property that will get used a lot, is if we have the expectation of some sort of linear combination, ax plus b. Okay, then we can take the A out and think of this as A times the expectation of X plus B. And if we wanted to find the variance over here, we could take the A out, but this becomes A squared when we take it out, and the B sort of disappears. Okay, because if you're taking the variance of a set of numbers, and let's say you add a certain number to them, suppose you added 5 to that entire set, it would not change the variance. Well, something like this happens here, and you could see that there's a proof of this in the class notes. Okay, so a couple of other items that are sort of a byproduct of expectation are related to covariance and correlation. Right? You probably learned somewhere along the road that if you look at X and Y pairs, you might say that X and Y are positively correlated if the scatter plot looks like this. This is a negative correlation, and if they're just all over the place, they're not correlated at all. So rho is the population correlation coefficient and measures the strength of a linear relationship between X and Y. But it's interesting, rho can get determined using the covariance, and covariance can be determined using expectations. Okay, so we define the covariance of x1 and x2. So this stands for covariance as the expectation of x1 minus mu1 times x2 minus mu2. But due to one of the properties I just showed you, this can be simplified to just e of x1 times x2 minus mu1 times mu2. So here you see covariance in terms of the expectation. And then we can get our correlation coefficient by looking at the covariance of x1 and x2 and then dividing by the product of these two standard deviations. So this is, if you think about the relationship between covariance and correlation, right there, they're somewhat similar. If there's a positive relationship between the two variables, both the covariance and the correlation coefficient will be positive. But you can see here, the correlation coefficient is always between -1 and 1. Okay, that's because down here we're dividing by this standard deviation, so you might say that this gets normalized, okay, to some value between -1 and 1. And one other item here, tying in independence, there's a theorem that we could prove in class. If x1 and x2 are independent, then the covariance of x1 and x2 is equal to 0. But I do make sure to point out that the converse of this is not true. If the covariance is 0, that does not imply x1 and x2 are independent. So this concludes the video. I hope you learned a lot from it and you go on and take a look at Chapter 5 material. I will say this, there are many examples in Chapter 5. So there are 2 videos that I have provided called Chapter 5 Examples Part 1, and then there's a follow-up Part 2.